Hello everyone, my name is Josh. I wanted to put together a quick video to demonstrate an interesting technique that can be used within Houdini to automate the process of authoring USD variants in Solaris, and we do this using PDG networks. Leveraging methods like this that use PDG allow us to very quickly generate any number of geometry variants and can be extremely useful for quickly creating assets for environment scattering and various other tasks. So let's jump straight into it. So I just want to do a really quick run through on how this is all kind of working, and then we can do a step by step on how this is all kind of put together. The example that I'm using here is something that I've just done quickly. It's using some of the labs nodes to create a chi generator. So you'll see that these are the nodes here relating to that. And then we also have a top net here. This top net here has a bunch of different things. So we've got a wedge to create some custom attributes, and then the ROP geometry output, and then also the ROP USD here. And inside we also have a stage, a Solaris stage, which is where we author the USD variants based on the tree geometry that we have. So just to go back to the beginning, I'm not going to go too in detail on how this is all set up, but you'll see that I've got some nodes here just to generate some trees. And then this first node in the top network is a wedge, and I'm creating 4 different wedge attributes here that we can essentially use to drive parameter values in our SOP network. So you'll see that I'm creating a tree height attribute, branch length attribute, main branches and number of secondary branches, and you'll see I'm essentially just asking tops to create a value, give me a value between 7 and 10 on 10 different items. So each of these dots here relates to a work item. So you'll see as I select over these, you'll see the attributes that we have here. So you'll see that I've got branch length, tree height, a bunch of different ones, right, that are all different values based on the work item that we have selected. So we can see how that works here. So I've got this node selected. If we go back here, I'll go on this one just because it'll be relatively quick, but obviously there's further attributes on all of the different nodes. So on this first one, we're referencing in that tree height attribute. We then also have the number of branch nodes here. So this is the number of main branches. On this third node, we're then using the number of secondary branches, and then a bunch of different things. We've got branch length here as well. I think that's being used in this first one. Yep. So you've got branch length here as well. So that's where all of those attributes are being used. But you see, I've got this second node selected. As I go through all of the different work items that I'm generating with tops, that you can see all have different values. You'll see that I get essentially a different variation of this tree geometry for each different work item, and that's what's driving USD variants. So we could have X number of work items that generates X number of variants, and this is very expandable, very scalable, right? So yeah, that's how that works. So that we essentially create 10 different geometry variants here, and then we're using a ROP geometry output to export those. In this instance, I'm using BGO. This basically just writes each model variant to disk. The wait for all just basically says before we do anything else, let's just wait for all of the exports to finish, and then have a ROP USD here that finishes this chain. You see that this ROP USD actually uses a LOP path, which is in this stage here. So essentially, we're telling it to run this stage and get the output, which is this node. And you'll see inside the stage we have a for each loop, and in the iteration number we are using that wedge total. So you'll see, if I select this work item, it might take a second to cook, and then view this, you'll see that we have a wedge count and a wedge total. That is essentially representing the total number of work items that we have. So we're saying, because we're generating 10 different model variants, we want to iterate over all of those variants, and this is our total number. At this point, we use a SOP import. This essentially just brings our geometry in, and I'm doing that using just a file node here in this SOPnet, and using an attribute wrangle just to give it some pathing parameters, but we'll go over that in more depth. But yeah, so that's essentially it. We then bring the geometry in using a SOP import, author the variant, and then this final ROP USD here in this network exports that tree USD to disk. And you'll see that if I go to my stage here, I've already brought this file in. I can reload it. I've got an explore variants here just to show you all of them, but this gives us a single USD that contains our 10 geometry variants for that tree. But yeah, so we'll go through a step-by-step guide on how this is kind of all put together, but that's just a quick overview. Cool, so let's go over this in a little bit more detail and go through it kind of step by step. I'm not going to go through the tree generator, but I will briefly go over how wedging works, just to kind of give that a little bit more of an explanation. So if we go over here, I'm going to drop down a sphere node, right? Let's just view that. We're going to make this, I don't know, 10 times bigger. Just going to use geometry for this example, and we're going to give it a bunch of frequency, give us more polys to work with. And then what we can do is use a mounting stop just to drive the position attribute. I'm going to change some of the values here. So for example, let's use a element size of 5 and turn up the amplitude a bit, right? So let's set this to 1. So this is going to give us some noise on this sphere. You can see that if we drive this offset value, we could give it an X number of different values. So we could say 1 or 5. This is going to basically give us a different variation of that geometry every time. So this is where tops is really useful. It means that we can create as many different variations that we want, right? So if we use a top net, I'm going to drop down another one here. And then inside this, I'm going to create a wedge top. Cool. So we can then create some attributes. So let's just call this noise offset. And then this is going to basically ask us to give it a range, and we want to turn on random samples. We want to say that we want to create a bunch of random samples between these two values. So I'm going to use between, we could do 0 and 100, right? So then if we cook this node, you'll see that we only have one value at the minute. That's because our wedge count is set to 1, but it's going to give us a random noise offset value between 0 and 100. So if I turn this up, we could have 20 different values. I'm just going to dirty this node, which essentially means get rid of everything and then cook it again. Now we have 20 different work items, and you see that as we go through on all of these different work items, we have a different offset value. Now we can use that value in our SOP network. So it's something called a local variable. So what we can do here is in this offset parameter, we can reference that local variable using the @ symbol, and then we've called it noise offset, and we'll drop that in here. And you'll see that that's automatically linked up. So we've got this first work item selected, and you can see the noise offset value here for this work item is 33.75. So we have 33.75 here. Now we could select all of these different values. So there's 97.98, 70 here, and you'll see that those values will represent in that parameter here. And we're essentially going to get a different geometry variation for each work item. So that's basically how wedging works, and what drives the different variations for our geometry variance in the tree example. So that's how that works. So once we've got our wedge attributes set up, we can move on to the next step, which actually is writing the geometry out to disk, and then those files are what we use to author the USD variance to a single file. So in order to do that, we use this ROP geometry output top, and this asks us for a SOP path similar to the USD ROP that we went over in the quick overview, and then also asks for an output file path. So what we can do here is we can ask to generate this node. Generating the node essentially says, tell us what we are expecting to get out for each work item, but don't actually cook the node. So if I generate this, you'll see that it's going to ask me to save, and then it's going to give me these 10 grayed out work items here. That's because it's not actually cooked those work items, it's just telling us this is what we're expecting, and that is represented. If we look at the work items, you'll see that we have an expected output. The cool thing about this is that we can reference the local value wedge num here. So if I go over each of these work items here on the wedge node, you'll see that for each work item we have a wedge num attribute. So the first one is 0, second one is 1, 2, 3, going all the way up to 9 in this example, because we have 10 total wedge attribute count. And then we use that for the file path. So essentially what is happening under the hood here is that we're asking to get this node, which is at the bottom of our chain here, and it's saying I want to basically run through this for each work item, which is why we've got 10 different outputs here, because it's coming off this. If we were to change this to for example 15, and we just cooked this and then generate this, save, you'll see that I now have 15 work items. So it's saying that because I've got 15 wedge total of 15 here, we need to generate 15 different geometries or 50 different outputs on this node too. So that's going to give us 15 different files. So I'm just going to set this back to 10. Let's just cook that real quick, and then that's going to do the same here, and then we can cook this out, and then that's going to write our geometry to disk. So I'll do that now, and then I'll come back when all of those are written. Cool, so now we've got all of those different geometry variations written out to disk, so we can move on to the next step, which is actually authoring the USD variance. So the first step to do that is we want to drop down a wait for all. This is basically going to say that before we start authoring the USD variants, we want to make sure that we've actually finished writing out all of the geometry variants to disk first. It's important to make sure that we don't start working on the USD variant authoring until we have all of those files, otherwise things are going to mess up. So we can cook this straight away. You'll see that we are just going to get a single output out of this, and if we go to the work item info here, we've got 10 outputs here that all relate to those files that we've written out to disk. Then we can drop down a USD ROP. So we drop down this top node here, we can plug that in, and it's going to ask us for a LOP path, which we obviously don't have yet, so we can get straight onto that. So if we drop down a LOPnet, this is basically just going to give us an empty USD stage within Solaris. We can get started by dropping down a for each loop, just like that, and we want to make sure that we set our iteration count to the same number of wedges that we have from our top net. So you'll see that our wedge count here is set to 10. That's generating 10 work items. And if we go to this wait all and view the work item here, you'll see that we have a wedge total of 10. So we can access and use that local variable in the iteration count here. So we can set this to wedge total, and you'll see that when we look at this, it's set to 10, which is the same as our wedge count from the top network. Now we can look at bringing our geometry in. In order to do that, I'm going to use a SOP network and a file node. So inside here, I'm going to drop down a file node, and we do something interesting here with the geometry file to make sure that we bring in each work item or each output file. So we can use a function called PDG input. So if I just drop this down here, it needs to be inside backward ticks PDG input. This is essentially going to say, look for an active PDG network, give me an index and the tag that you want to return, and I'll load that file path. So the input that we want to get, or the work item number that we want to get, is based on the current iteration that we're working on within that loop. So we can use a context option expression here, and then set this value to iteration. And then this is basically going to say for each iteration of the for each loop, return the value of that, or return the iteration number. So as we go through from the 10 values, or the 10 loops that we have, we're going to return 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's then going to relate to the work items that we have in PDG. And then we need to pass it a tag. So this is what we actually want to load in from that PDG input. And in this case, we're going to load in file geo. And then this is just a serialized or a localized thing here. You don't need to worry about that one. So we can jot that down. This is going to error because we haven't actually written anything out yet. But you'll see if I go back to the top net and I look here, just to show you how that tag is working. If we go to our output section here, you'll see that all of these files here have a file geo tag. So this this expression here is basically saying for each work item, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 that we loop through on the iteration, return that file geo path. So that's how that works. That's how we can bring all of those different files in. I'm then going to drop down a wrangle that runs over prims, just because I want to set my paths for USD. We can pass a path attribute on a primitive and then use that to create our primitive paths in USD. So I'm going to just create this really quick. I want to give something a name. So the name here is just going to be tree mesh. So I do tree underscore mesh, and then I want to pass a path. So path equals, and then I want to make sure that all of this goes underneath a geoprim. So we can do it like that. Cool. So that's going to author our primitive paths in USD. Then we can drop down a null and call this geo out. Cool. And then inside this LOPnet, we can drop down an add variant because that's what we want to create. So we'll drop this into the chain here. This is going to be our input stage and also what's output here. And then we can start filling some of this stuff in already. So we want to make sure that when we write this, these variants out, they're underneath the tree primitive. You can change this based on whatever you're doing. But obviously, because we're working with the tree example here, I want to make sure that all of my variants are authored to this tree primitive. And we're going to write it underneath the model variant set. Now, in order to bring those the geometry in, obviously we've brought it into the SOP net here, but we want to bring it into LOPs. I'm going to use a SOP import, so that allows us to bring a SOP node and bring the information in. So I'm going to drop that down and we plug this into the input, the second input for the add variant. It's going to ask us for a SOP path. The SOP path that we want to pass is this geo out node here. So I copy that, drop that into the SOP path. There's a couple of different workflows for this that I've seen. Some people make sure that they have the layer path, layer safe path set. This essentially is going to author a or write out a USD for each geometry variant. Now, for this, I don't want to. I want to make sure that all of my geometry is just written to the file. I don't want to have 10 different files for the BGO geometry and then additional 10 files for each of the USDs that we then reference in. I just want to write everything to a single USD. So we can do that by changing the sublayer style. So we change this from add SOP to layer as a new sublayer, and we do copy SOP layer into a new active layer. And then that's basically just going to write all of our information to an implicit layer rather than having to reference a file that we save out. So we can turn this off. On top of this, we want to make sure that we set the import path so it's consistent. So I want to make sure that I'm importing all of those, all of the geometry in underneath the tree, and then I'm going to give it the pass through the context option again. So essentially, this is going to say for each geometry that we bring in, we want tree 0, tree 1, tree 2, tree 3. So we can add the iteration there. Cool, and then we can go back to the add variant. We want to say that we always want to bring this prim in. This is going to be our source primitive. So we copy that path there. You could even channel reference it if that's what you wanted to do. And then we do, because we're looping, we want to set a variant name default. By default, this is the name of the SOP or LOP, sorry, that comes previous to the add variant, but we want to author this manually. I want to make sure that it's called, that the variant names are called tree 0, tree 1, tree 2. So I'm going to copy that and paste it here. And then that's basically the setup. We drop down a null here just at the end. We're going to call this USD out. And then if we copy this node, pop it into the USD ROP here, into the LOP path, we can then write an output file path. So I'm going to just find where I want to export it inside here, and then we're going to write this to tree.usd. Cool. Then we can just cook that node. So if we press cook now, it'll probably take a little bit, and then I'll come back when it's finished writing. Cool, so now that's finished writing out, we can go to our Solaris stage. We can put down a sublayer and bring in that file that we've just written out, this tree USD. And you'll see now that we have this tree prim that has a model variant set that has variants tree 0, tree 1, tree 2, tree 3, and so on. We can view all of these by using an explore variant LOP. So if we drop this down, change the mode to explore variants, and I want to use bounds, you see that then we can see all of the variants that we've authored underneath that prim. Alternatively, if you want to just change a single variant, you can use a set variant here. If we grab this tree primitive, you'll see that we've got the model variant set selected here, and we can go between all of these different variants that we've authored here. So this is really useful for layout. There's also another setup that we can use that's a little bit more complex that we can use to author different types of variants on top of this. So we'll go through that now. Cool, so coming back to where we were previously, we could talk about how we want to author different types of variants as well as just the different wedge values. So in this example here, we could say that actually these variants here all have leaves, but we actually want to author some variants that don't have leaves. So we'll drop down another null, and what we could do is we can take this input before the leaves are generated. So you'll see that if I pass this through here, these are exactly the same in terms of the height, the branches, all of the wedge values that we have here, but these ones don't have leaves and these ones do. So we'll just name this null just for organization. We'll do tree geo no leaves out, and we can expand upon the network, the top network that we already have here. Cool. So these two nodes here are obviously handling the export of the geometry for the leaves, or the geometry that has leaves. So we could just move those to the side, move this down, and we'll just copy this, and we'll expand upon what we've already got. Cool. So we want to change the SOP path that we've got here to be the tree geo no leaves out. So we'll go in here and change the SOP path. We also want to change the output file. So instead of writing it to the same files that we had before, let's write it to, we'll just add no leaves in there as well. And we want to make sure that we've got this wait for all as well. So you'll see that if I just generate this, you see that I'm also going to get an additional 10 work items here, and all of these aren't going to have leaves, and these ones are going to have leaves. We're going to wait for all of those outputs to finish, and we're going to merge them together. We generate this. You'll see that we get two work items here. The first work item relating to the 10 outputs that we have on the left that do have leaves, and then the second relating to the 10 outputs that we have on the right that don't have leaves. The important thing that we need to do here now is do another wait for all. This is essentially going to make sure that our outputs are all in the right order. So if we generate this node here, click save, you see if I view this work item here, I then have 20 expected outputs where the first 10 are the tree geo, obviously the ones that do have leaves, and then the following 10 outputs are the ones that don't have leaves. That's important because we can essentially keep the iteration number the same, so we want to iterate over the same time, but we want to get the second 10 outputs instead of the first 10. I'll show you what I mean by that now. So we can hook all of this up, go into our LOPNet, and the setup's going to stay pretty much the same. So we can go into our SOPNet now. Obviously, this here is only going to bring in those, because we're only looping over it 10 times, this is going to bring in our first 10 inputs, which are obviously the ones with leaves. So we can copy this, and then in here, all we want to do is we want to add 10 to the context or the iteration number here. So instead of bringing in 0, 1, 2 all the way through to 9, we're going to bring in 10 through to 19, or our 10 to 20 on our PDG input or outputs, which are the geo files that don't have leaves. We want to keep all of this the same, and we'll just name this to geo no leaves out. Cool. And then we'll go back into this section here. We can keep all of this the same. We're going to just bring this down, and essentially we want to just duplicate this, so we have this exactly the same, and what we want to do is, instead of getting this geo out from here, we want to actually swap this to the geo no leaves out. So we'll just swap that out, and we can keep absolutely everything the same. So those variants are all going to author the same way as they were before. And then on top of this, we'll add an add variant. We want to create a new primitive. Again, this is going to be our that's going to be our input there. We're going to hook this into the output, and then we're going to hook our add variant into the input of this additional add variant here. We want to make sure that we author this underneath the tree primitive, because that's what we had before. Our source prims are what is going to be set to tree here, because we want to make sure that we're bringing in the correct prims. So we will copy this and paste it here. And we don't want to use the variant name default. I'm just going to remove it for sanity's sake, but we can change this first input here to be leaves, because it's relating to this first input, and this is the one that's bringing in the geometry variants that have leaves, and the second one is going to be set to no leaves, as so, because that relates to the SOP input here that brings in and authors the variants for the ones without leaves. And then that's it for our setup, other than the fact that we can just change this quickly. We want to set this to type. So this is going to show us our different models. That's going to relate to our height, our number of branches, the branch length, etc. But then this variant set is going to relate to the type, so whether they've got leaves or whether they don't have leaves. So then we can go back to our topnet and we can cook this out. I'm going to do that now, and then we can take a look at what we get for our USD output. Cool, so you can see that our USD is now written out. So we can go into our stage network here, into Solaris, and drop down a sublayer. And again, we're going to bring in that tree USD file that we've authored and written out to disk. You see already that this has worked. We can use an explore variant, and we can look at everything that we've got here. So let's change that to explore variants. We want to use bounds, same as we did before. And this time you'll see that we have 20 variants authored to this prim. We can go through these individually as well, and it's really cool to see how this all works, right? So if we use a set variant here, what we can actually do is we want to set this number of variants to 2. We want to pass the tree prim through to both of these. This first one we're going to set to type, and the second one we're going to set to model. And if I view this, cool. Let's just set this to tree 0 and first leaves, right? So if we select leaves, you'll see that for this we have 2 different types. We have with leaves and without leaves, and then this follows through for all of our different trees, right? So the branches and the actual model itself stays the same. We just decide whether they've got leaves or not now. So it's really cool, really expandable. We can also use this for scattering, which is something that I'll show you in a moment, or just layout in general. And it's really useful for quickly generating variants that can be used for things like environment scattering and different tasks like that. Cool, so I've just done a quick setup here to go over how we can use those variants that we've authored with PDG to really easily create a scatter for our environment. So I've brought in the tree USD as we did before. I'm using an explore variants. This basically allows me to look at all of my variants, but I'm making sure that all of these go onto the origin. This is important because it basically means that we have access to each of the variants written out here as an individual prim. Just to make the instancing a little bit easier, I'm using a collection. So I'm writing all of the variants, all of the prims that are inside this tree prim here. So that's all of these here, as the primitive here inside a collection called tree variant. Cool. So then I'm flattening the stage, and then inside this instance, I'm just creating a grid with scatter on it. You see that I've just got points here, and then we can use the second input to source our prototype primitives. And then the actual prototype primitives that we want to get are all of the prims that are part of this tree variants collection that we created here. So you'll see that when we view this instancer, we then really quickly get a scatter here. Obviously this is just a quick job, but you could scatter this on an actual environment properly. But you'll see that it's really easy for us to very quickly automatically generate PDG variants. So you could go back, change the wedge values, recook this out, reload your USD file, and all of these are going to update. So it's really useful. Hopefully this video has been useful, and it's been good to look at some insights. I'd appreciate any feedback in the comments. If anyone's got any questions, feel free to ask and I'll reply as much as I can. But yeah, thank you for watching, and I'll see you in the next video.